David Vizard here, and you are watching PowerTec 10. Give me a few moments of your time, and I will give you the benefit of over 60 years of building high performance and race-winning engines. I have to warn you, this PowerTec 10 may be more like a PowerTec 30, but I guarantee you're going to learn a lot from it. Give me a little of your time, and I will show you from my 50 years of race-winning engine building experience how to get more out of your performance engine. Today's subject is valve springs, and believe me, there's a lot to learn. On the face of it, coil spring looks like a pretty simple thing. I mean, it's just some good quality heat-treated wire wound in a coil so that when you compress it, it exerts a load. Many enthusiasts will assume that if a spring gives the right preload on the valve seat and the correct over-the-nose spring forces, then it's okay. And that's it. But no, there's a lot more to it than that. If you know these other things, you can make your spring selection a deciding factor in whether you have a winning engine or an 8th place engine. But the hot rod industry doesn't stand still. It moves along because competition is stiff. Advances are made almost as fast as they are in the aerospace industry. The question is, yes, this was a good spring back in 1995-2000, but can we do better than what we see here? Well, the answer to that is we certainly can. And that's where we're going to go now. Here's Comp's 924 spring. That's the one we've just been looking at. Here's the retainer for it. Now let's just weigh that and see what we have. That comes to a total of 142 grams. Right? Well, a little over. This beehive spring will replace that, and here's its retainer. See how small it is? Now let's weigh those two. 85 grams. That's a 40% reduction in weight. That's equivalent to swapping all your steel valves for titanium valves. Here is an even more advanced spring than the beehive spring we have here. Now this is a stiffer spring here and it's meant for higher RPM. But look at this. That's only 76 grams. And it will outpace this spring very, very easily and by probably a 2000 RPM margin. To see why, let us now go to the spring tester. Well, here we are at the spring tester, as you see here, but before we get going on that, let me tell you a short story. In the late 90s, that's 98, 99, I was involved with quite a lot of valve train testing for pro stock stuff. This was all prompted by the fact that spring breakage was very, very common. It was a big problem. For instance, even with the best springs out there, in 10 runs, a pro stocker would have, on average, about 15 valve springs replaced. So we're looking at the destruction of more than one valve spring per run. So it can't possibly help power as that valve spring goes away. It's going to allow valve float and things like this to happen. You'd never hear it because of all the other noise. But nonetheless, this problem had to be solved. And the question was, what could we do? The answer to that is a lot. But it takes a driving force behind it. And this pro stock deal was really a major issue. And this pushed spring manufacturers into looking at better material, different designs of valve springs, different wire designs instead of just round wire but shaped wire, and so on and so forth. And certainly by 2005, the issue with valve springs breaking as often as they did was largely overcome. So how was it done? Well, that's what we're going to look at. So let's get with this spring tester program right now. What we have here is the valve spring that I showed you, and I introduced it as a basically regular valve spring, but a good one for strip applications. I'm going to test it on the spring tester, but first you need to be able to set the spring height to set the seat preload. Now this is often called the seat pressure. That's not exactly the right word to use. It's seat force, or the seat preload. Pressure is pounds a square inch, and we're going to be looking at pounds here. Anyway, enough of that. This is a relatively inexpensive spring setup tool from Comcams, right? And we're going to set the spring tester and zero it out. So that's to do next. Right, our installed height for this spring will be 1.8 inches, and the retainer takes up another 1/10 of an inch at the top. So I've set this gap here to 1.9 inches. Let's see what our spring delivers at that. Right, here we go. So the seat preload on this is 140 pounds, right? Now then, let's have a look at what we would see as a typical over-the-nose force on this. A good strip motor, like a small block Chevy 383 or such, is going to need somewhere in the 600 to 650 lift rate. So let's see what this delivers. There's 1, 2, 3, 4, 5, 6, 125, and it delivers 350 at 625 lift. And you'll notice that it's fairly close to coil bind here. Here I want you to watch how each individual coil separates from its neighbor. As I lift this up, you will see that nearly all of the coils, except the top 2 and bottom 2, are working coils. In other words, almost the whole spring was still in action. I want you to keep that point in mind. It might seem like I've been wandering around the subject at the moment, but now we're coming to a critical point. Remember, I gave you some weights earlier on of our regular spring versus a beehive versus a taper spring. Now, we'll come to the significance of this. With this spring here, during its operation, almost all of the coils were in action. That meant that the weight of the spring, the actual spring part of the entire entity here, was in motion. So, being as this is a heavier spring, there was more mass in motion, right? And each spring has to have enough going for it to be able to control its own mass, as well as the mass of the valve train. Now, the lighter we can make that mass, the better. The more RPM we'll get, and do so with lesser spring. For instance, the first thing that a lot of people do with a spring like this is use a titanium retainer. That's a good move, but these aren't cheap. There's a better solution. let's look at our beehive spring. Well, first off, the retainer for a beehive spring weighs about the same as this. This is a steel one. They don't cost much to make out of steel. So that's the first move. Going to a beehive spring means that the retainer now is the weight of a titanium retainer had you stayed with that. Next thing is, let's look at how these coils compress. And you'll realize that there's another attribute there that is well worth having and will significantly increase the RPM to which a spring of the same kind of capability in terms of delivering force will allow the valve train to go to. That's what we'll look at now. Before going to the spring tester, let me just run through a few of the design advantages of this beehive coiled spring. Firstly, the material it's made of is significantly stronger than it is with this spring. The result is that we can make a spring of a smaller diameter out of thinner wire. Those two factors there allow us to make a lighter spring for the same force delivery as this more conventional spring. Also, the fact that we use less steel in it means that we save money on material costs. So even though this is more expensive metal, we're using less. Next, well, let's look at the coil spacing here. Other than this first coil here, which is shaped like this so that the spring seats down and has a flat surface, and that's both ends that occurs, we see that the parallel section, which is about that, the coils get further and further apart. Once it gets to here, the diameter starts to get smaller. Right? Now what this does is it gives us a variable rate spring. So when this spring is compressed, the coils settle down on each other progressively, therefore taking those coils out of the spring equation. In other words, once the coils become bound, they no longer represent a mass that the rocker has to move. That has very strong implications on how well this spring works. But a couple of more details, right? The spring section is not circular. It's an ovate form, and the metal is placed in such a position that it is better able to take the stresses. In other words, the metal is where the stresses are, not where they're not. So the material in this is performing at a higher efficiency. Now let's go to the spring tester and see where we are at with that. Here we are at the same fitted height that we used to test our previous spring. You'll notice we're looking at almost 150 pounds on the seat. So that much smaller spring with, in actual fact, less compression on it, because it's also a shorter one, is delivering more poundage. Right, now let's pull this up to 625 lift and see where we are. There we go, 625 lift. We have 360 pounds over the nose. In other words, we have a spring which can deliver slightly more than our previous spring, but using a mass something like 40% less. Now let's take a look at the coils and how they separate. What we see here is all of these coils are compressed, and one is seating on the one below it. The first one to have a small gap is this here, slightly bigger gap here. This spring is almost coil bound, but only the top two coils are actually working coils now. This means that as the cam goes over the nose, the spring involved is a very light two coil spring that's very stiff. right? So control of the valve train in terms of valve bounce is very good because it'll have the highest preload on the valve train at full lift. Now watch what happens as I slowly release this. You'll see that the springs progressively open up, bringing more and more of the spring into operation, right? And that's where we're back on the seat at that. What's the relevance of this? That's what we'll deal with now. When I've mentioned light springs and heavy springs, that is not me defining how stiff they are. That's talking about them in terms of their mass, i.e. what they weigh on the scales. Why is this so important? Well, that's to do with a factor known as natural resonant frequency. If we've got a spring which is very heavy in terms of the weight of that spring, then we find that the spring is going to have a low resonant frequency, right? That resonant frequency will be a function of its mass and its stiffness. Ideally, it would be nice to have a spring which didn't weigh anything, and then we'd have no problems with it doing exactly as we wanted. But the biggest factor with a spring is designing it so that the spring's motion isn't interfered with by the spring itself. That comes about by having a spring of the highest resonant frequency possible for the valve train. Ideally, now opinions vary on this, but ideally the resonant frequency of the spring needs to be about 10 times higher than the frequency with which it's opened. In other words, if we've got an engine opening the valves 50 times a second, then we should be looking at a spring, ideally, of 500 hertz. That is, putting it into more understandable language, 500 cycles a second, or 30,000 cycles a minute if you want it in minutes. Some spring catalogues, very few, but some spring catalogues quote the frequency of the spring in cycles per minute. Now, with this type of spring, the resonant frequency doesn't change very much. This spring here has a resonant frequency around about 450 hertz, or 450 cycles a second, right? It does change because we have got a certain degree of variance in the spring pitch, right? But basically, it doesn't change that much. Over its opening envelope, the resonant frequency of this spring may go from something like 350 cycles a second to around about 550 cycles a second. On the other hand, this spring here, which delivers slightly better or slightly higher seat and over the nose forces, has a frequency which starts off at about 350 hertz, but at 625 lift, it's almost off the chart. Up here, it's going to be well over 1,000 hertz. This makes it a spring which is able to look after itself when in motion, far better than that spring there. So it's not just a case of having the ability to turn more RPM, but it's also a case of having a better controlled valve train on the way up to valve crush speed. With this spring here, we're not going to get those little blips in the lift curve that cause the valve momentarily to pop off the seat, right? So less spring force needed to get the job done. The spring force happens where it should, and it'll go to higher RPM, right? All of those factors contribute to having a valve train that's better behaved and will make more power. But let's go and look at this resonant frequency a little more. Let's look at this spring's possible successor. That is the tapered spring. That's what we'll deal with now. This is our tapered or conical spring. Basically, what it's doing is it's taking the best assets of the beehive spring, and that's the tapered bit here, and doing that with the whole spring. This spring is about 90% of the weight of this spring. And although it's only slightly thicker in wire, it's a very much stronger spring in terms of what it delivers. Also, its resonant frequency is higher than this, so it's all good. Let me say a little bit more about our beehive spring here. This spring is in fact one of the most versatile springs in Comp's spring arsenal. It's recently been updated. It's the 26918 spring intended for the LS engine. I found these to be very useful on everything from big block Chevys to LS engines to small block Fords and Chevys, and in every occasion it's performed extremely well. It's a very good buy for the money. A bit more than our regular spring? Sure. Quality always costs money. But this is the real deal. Now let's go on to our tapered spring here, and we'll look at the loads that this can deliver. Here we are with our conical spring preloaded to 150 pounds on the seat. Now remember, this is actually a lighter spring in terms of mass than the beehive spring. Now just watch this. I'm going to lift this, not 625 but 650 from here. I want you to watch how the coils close up and watch how the load goes up. Here we go. 100, 200, 300, 400, 500, 600, we're at 460, here's 625 where we were with the other springs, just shy of 480, and 650, which is about as much lift as it will tolerate. You'll notice that the coils are almost coil bound, and at this point the resonant frequency of the spring is almost off the chart. Right, so good spring. So who uses these springs? Like I said, who uses these springs? Well, they may look to the general public like it's a pretty new thing, but in fact conical springs like this have been used in cup cars as far back as 2005. And here's the real interesting thing. It's important to note that you can get them in doubles. Now here's the good thing about these double conical springs is because the resonant frequency climbs so quickly, any vibrations that the cam and valve train tries to transmit into the spring are quickly gone through, so they don't reside in the spring for any measurable length of time, just an instant. And the fact we have two springs here with very different resonant frequencies means that the spring as a whole tends to fight surge very well. But let's go back to our beehive spring here. Right? Now, this sounds like it's a pretty good piece of technology here, but the thing is, it's not new. The Wright brothers used beehive springs on their the Wright flyer engine back in 1903. Right? Sure, not made as good material, not as sophisticated and things like that, but nonetheless. And GM have been using them on their mainstream production line engines, or at least many of them, since the mid-80s. The LS spring is a beehive spring, and that's a motor that's now been produced in huge numbers. But anyway, let's go and look now at some graphs to show the differences between these springs here in terms of their rate, their resonant frequency, and the change in their stiffness as they go to high lift. That's what we'll do now. So far we've looked at what these different designs of springs, all intended for about the same kind of application, what they will do on the spring tester. And we've looked at a bit of the theory behind it. What I want to do now is to put it in a graphic form. But what you'd be overlooking is that the beehive spring is doing the job with 7% more available spring force and 40% less weight. That can be worth a lot. Now let's look at the conical spring. From the red curve, you can see that this spring delivers a lot of spring force, but not much mass of valve. Remember, the beehive spring was like 73 grams, but the conical spring was only 68. Big delivery, not much mass. That's got to be good. To see how that translates into spring rate and resonant frequency, we'll go to the next graphs. Here we are at our spring rate graph. If you look at the black line and blue line, that is the dual spring, the damper, and the conical spring, you'll see there isn't much difference. However, as we approach the end of the lift curve here, you'll see that the conical spring's spring rate, as its stiffness, climbs very steeply. This is the advantage of this type of spring. When we're up here, the resonant frequency will be very high and it will tend to quench any large amplitude resonant frequencies from a lower lift point. So, this here shows us that our beehive spring can, in terms of poundage over the nose and on the seat, directly replace the 985, but it'll also replace the 924 spring. Our conical valve spring is very stiff. It's ideal for a very aggressive cam profile that also needs to turn a lot of RPM. So give that spring a consideration when you want an all-out valve train that you still need to turn maybe as much as 9,000 RPM with. Here are the curves for the resonant frequency of our three test springs. As you can see, when we look at the resonant frequency, we really separate the men from the boys. You can see this is the conventional spring, and this is about the same for any double coil spring you may go through. They don't vary much from this. Here's our beehive spring. Significantly better, and the more lift you put into the valve train, the better it becomes. Right? That is why it's important with a conical valve spring to utilize the spring within about 25 thousandths of its coil bound height when the valve train goes over the nose. Okay, you may have a little too much on the seat at that. It's better to have a few more pounds on the seat than it is to fail to utilize this characteristic here. This is what makes the beehive spring really work. Now, if we move on to the conical spring, you can see that this is an elite of its own. Now, these are just starting to come out on the market. So, if you're calling for a camshaft and things like this, you might want to check with your cam supplier whether this type of spring is going to be good for your valve train, well, for the cam profile that you choose.